Hello everyone, welcome to our graduate Capstone Spring 2022 Mobile Edge Computing for Traffic Management Mechanism using High Altitude Platform Station, which is HAPS. So we are a team of three people, Chaitanya, Gayatri and Shalaka, and we are guided by Professors Animesh Yadav and Sumit Chakravarti. So in this project, we have done with introduction, progress of the project, related research, and came up with problem formulation. The finals goals need to be achieved, the challenges faced, and a future plan. Overview of the project. Mobile edge computing is a new paradigm to accelerate artificial intelligence applications by leveraging computing resources on the network edge and can be used to improve intelligent transportation systems. HAPS, which is High Altitude Platform Station, is deployed in stratosphere to provide wide coverage and strong computational capabilities. It is suitable to coordinate terrestrial resources and store the fundamental data associated with ITS-based applications. Performing data offloading at roadside units, which is RSUs, in a cooperative manner can reduce the heavy backhaul load and the transmission of content downloading. In So in our project, we have come up with roadside units, which is RSUs and HAPS, and are integrated to build a computational framework for ITS, where HAPS and RSUs data library stores the fundamental data needed for the users, which is connected autonomous vehicles. We are analyzing computing offloading policy to minimize the low latencies and high bandwidth services to minimize the network energy of the CAVs while satisfying the constraints of the latencies, energy consumption, and the computing capability of MEC servers. Okay, this is next slide. Okay. Coming to a system model. This is a system model where we have considering one HAPS and RSUs can be multiple RSUs. So here we can see two RSUs we are represented, which is roadside units, and cars are considered smart vehicles, which is connected autonomous vehicles (CAVs). So in each area, RSUs are set up, and each RSU can take the approximate area of number of CAVs, where it can collect the CAVs data, and it can perform the computation offloading. And if in other area, RSUs will collect other number of vehicles so that it will do computation offloading and get to know which area, which route the vehicles can take if there's any collision or like any uh, hazards in between. So this is our system model. Okay. Each overview of a project is finally like each RSU will perform edge computing and it will interact with the smart vehicles and get the data with nearby roadside units. Each RSUs will share information with neighboring RSUs. If there's too much of data on single RSUs, it can offload to other RSUs. If one RSU is overloaded, it will pass the work to the nearby RSUs to avoid transmission delay and high offloading cost. If all the RSUs are busy, the CAVs can connect to the HAPS. HAPS will perform the task and transmit data back to the requested RSU. In that case, HAPS may be overloaded with data from a large number of RSUs. Next. Okay, coming our research problem. Because of the difference of scale, diversity, and timeliness of the mobile edge computing server has a great difficulty in processing and analyzing this data. So we have come up with optimization problem where we can use big data and and store resources and also do computing offloading. The computation results of time are time lag and retention and reuse of the data are often ignored if by using mobile edge computing. To address these challenges, in this paper we are focusing on minimizing the delay of the system by optimization computing offloading and as well as improving bandwidth and energy efficiency. The simulation results highlights the benefits of using HAPS for mitigating delays and the significance of caching at network edges. We have already has some related studies in regard to this paper. Artificial neural network, k-nearest neighbors, fog computing, and reinforceable intelligence surfaces. So since we are using big data, these studies showed like a lack of time delay and energy consumption. So we are coming up with the optimization problem in this paper. Coming to a problem formulation, we will here describe our system model including network, communication, computing model. Then we formulate the data in detail. This table represents a notations of each equations where M is represented as number of RSUs and N is the number of CAVs. Coming to a network model, the task of CAVs, which is autonomous vehicle, is represented in a set which indicates the size of input data, and we are doing computation in 3 levels. One, computing at local, where we are considering q as a variable and which equates q equal to 0, which means it is computing at CAVs at local, and when q equal to 1 it is computing at RSUs, and when q is equal to computing at HAPS. The following conditions must be satisfied. The following conditions must be satisfied in the equations 1 when dealing with these 3 levels. And here is a matrix, for example. So each columns should be less than or equal to 3 because delegating task at 3 levels at HAPS, local, and RSUs. And the number of rows are associated with the CAVs with the RSUs. For example, if you see for RSU equal to 1, here CAVs has 3 phases to delegate. First is to the CAVs to CAVs, and second is to the RSUs, and third is to the HAPS, CAVs to HAPS. So number of rows depends on the number of CAVs associated to a particular RSU. And similar way in the next matrix, we have done in the same way. And finally, we have come up with the time delay in each levels. So time delay at local computing is performed as Tmi of 0 is equal to Cmi denominator Fmi, where Cmi is the computing workload of CAVs and Fmi represents computing capabilities of CAV at nth. Next is a time delay if the offloading is done to neighboring RSUs. The equation is given in here. So in this case, we are considering time delay in three phases, like transmission time from CAVs to RSUs or RSUs to RSUs, and TCO represents the round trip, taking time from one RSU to other RSU and sending back the data. And T execution is nothing but when one RSU is busy and it will be executing other RSU. Next stage is the time delay. Next is time delay if the offloading is done at HAPS. Here also the time is defined 3 stages. One is transmission time and other is a round trip, and one more is execution. We can ignore the round trip here because when CAV sends the data to the HAPS, we are not delegating any more data from HAPS, so we are ignoring the round trip. So we can consider here transmission and the execution time here. So these are main equations for the time delay at each stages, and next we have come up with the similar equations for the energy consumption at local computing and at RSUs and at HAPS. So EMI at local computing, we have come up with formula K, CMI of M square, this one, where K is nothing but is a constant which represents the energy conversion efficiency relying on the architecture, where we can set K is equal to 10 to the power minus 11 as per the actual measurements. The following energy is also calculated when CAVs are directed to RSUs, and this equation represents the energy consumption at RSUs. And similarly, we have come up with the energy delegated the data from RSUs or else from CAVs to HAPS. So all these equations, time energy and energy, we are considering here, and finally we have come up with minimizing the problem formulation. Over to you, Shalaka.
So in this, we are formulating the collaborative data caching and computing offloading problem to minimize the total cost of all the CAVs. And we denote that offloading decision and uplink transmission power policy and computing resource policy as the given MINLP problem, where we have X, Y, P, and F. These are the X is the offloading decision, Y is caching decision, P is uplink transmission power, and F is computing resource policy. So it can be seen that the objective function here is the weighted sum of the delay and energy consumption of all the users. So here the key challenges of this optimization problems are that firstly, this is a MINLP problem, which is
Mixed integer non-linear programming
problem, which is NP hard due to the constraints with the discrete binary variables. And also in addition to this, since the objective function is a combination of all the variables, it is very difficult to solve in polynomial time. So here we are by using the scaling techniques and relaxation method, we decompose the original problem into two sub problems, that is convex optimization problems. So we will be splitting the main problem into convex optimization problem, and then we will apply Lagrangian dual approach for minimizing the delay in our formulation and minimizing the constraints. So this is the conclusion. Here we are minimizing the delay in our computation offloading. We have also the conclusion here is the key challenges of this problem. We investigate the optimal bandwidth and computing resource allocation problem with the offloading policy, and also utilizing the Lagrangian dual approach to define the problem's KKT conditions. And then we'll use bisection search method to obtain the closed form solution for bandwidth resource allocation and the optimal solution for computing resource allocation. We formulated the problem as a delay minimization problem, that is MINLP, where we first focused on optimizing the computation offloading and then focused on the allocation for bandwidth and computing resources. For now, we are just reviewing the optimization methods and implementing the next phases. So in conclusion, we are currently working on minimization problem, MINLP problem solving through relaxation and Lagrangian duality decomposition. We obtain this optimal solution to the first subproblem as well as the solution to the second subproblem can be obtained by dynamic programming. Further, we are also looking into a heuristic algorithm if that can be used to solve this problem, which can significantly reduce total cost and achieve better performance than other methods that we have just given in the research related research.